Is that again? Can you just like yell at me? I can't really see from over here. So it needs this one. Hello? Cool. Is that working? Hi, my name is Joe Rosner. This is SynFuzz, Building Language-Aware Fuzzers. This is a highly condensed version of the abstract that was in the program. There were some scheduling conflicts that necessitated turning this into a stable talk. Oh, is that better? Apparently. All right. Let's see if that will stay. So I tried to keep in all the relevant information. If there's something you're lost on, just yell, and I will explain. So to get started, if you've ever tried testing software with really highly structured input data, you've likely run into a handful of problems. And ultimately, this comes down to the fact that testing structured input is really hard. And examples of this are things like compilers, interpreters, complex network protocols, things that have really structured data where there is maybe information that is in one part that's going to be used somewhere else to determine how to continue to unpack or understand something. Terminal menus, if you're in interactive programs, places where you really need to make sure that you're testing like the right series of things that get you to a place in the application that will have some kind of interaction. And it's hard for a handful of reasons. The first being that simply getting your test cases is a really hard thing to do. If you've ever worked on software, you know that test cases are not always super common, and depending on how strict your team is, you may or may not have good test coverage. If you're in open source, you kind of have the benefit of getting access to the actual test cases, if they exist. If you're working on, say, reverse engineering something, or you are trying to determine whether or not something you're building is going to be compliant with something else out there, you might not have the closed source test cases. It just is part of the actual product's source code, and you don't have access to that, so you're kind of limited in what you can get access to. Understanding code coverage is sometimes difficult. There's a lot of tooling out there that will inspect the application, will trace execution through there, and kind of show you where you have explored in the application. But that's not always available, and just because you've been to a place doesn't mean you've really exercised it. State is a thing. It's very rare that you see truly stateless code, and so just because you got to an area with some certain state does not mean that different state will not have some completely different behavior. High code coverage does not, like I said, does not always equal well exercised. And so like if you're trying to test a parser or something that uses a parser to validate input, if you don't get past that initial parse, you might not ever get to anything interesting in the application because it's that gatekeeper and it's stopping you from getting to a place where that information is being used. So you want to avoid uninteresting input, stuff that's not going to get you past that point. And so typically a lot of off-the-shelf fuzzers and tooling out there is going to look for very specific conditions. Looking for cases of, did I crash the application? Did it end in a seg fault? Did it end in a sig abort? What's the return value of the application and what did it do? So you've limited flexibility in determining, your failure cases and understanding, did that do something interesting and do I want to continue down this path? You also have pretty limited flexibility typically in creating that feedback loop in terms of how you want to modify your input for that next iteration as you generate your next input. So that next mutation you're going to perform to the input to see, am I doing something interesting now? A lot of the time, as we'll see, they're just based on randomness and a handful of other techniques. But ultimately, for any sufficiently large or complex program, you're probably going to want to use some sort of automated test generation. Fuzzing is just one of those ways you're going to become effective in trying to get good coverage and understand that you feel comfortable with how much you've tested this. It's the only way you're going to get billions of test cases out in any reasonable amount of time with a reasonable amount of work. There's a lot of different ways you can do this, and a lot of different techniques. We're going to focus on grammar-based fuzzing, and essentially what this does is it takes a grammar file, and when I say grammar file, when you're building a language, you typically will define a grammar, whether it's context-free or regular or context-sensitive or Turing-complete, but you're going to define this grammar. And if you're using a parser generator, you're going to feed this grammar in, and it's going to spit you out some code that will recognize that language. So we're going to take this grammar, and from that grammar, we're going to do the opposite. Rather than trying to parse input, we're going to generate input from that grammar so that we know that it's syntactically correct, and we don't have to worry about that case of sending an input that's not getting us past that initial parse phase, at least hopefully. As I've said, if you're using these tools, they all have their own grammar definition languages. So whether you're using like Bison or Yak or Antler or any number of these different tools out there, they're all going to be subtly different. Their parsing algorithms are different. The actual definition language is different. And because of that, you typically, for the tools out there, need to end up rewriting a lot of these grammars in the very specific language that the tool expects. So examples of tools that do this are Mozilla Dharma, which is an open source project that they use for testing browsers, so for HTML, CSS, JavaScript. There's also a really great paper called Fuzzing with Code Fragments that introduced a tool called LangFuzz, also out of Mozilla. This is not open source, and as far as I know, it's not available generally. Both are really good places to start looking at for more information about how this works. But the idea is they both take these specific grammar languages where you define your grammar, and you have to translate the grammar that you're working with to this language. And that's not necessarily an easy thing to do. You're talking about grammars that might be tens of thousands of lines long, super complex, and maybe the syntax or the semantics of it are subtly different from how a different one might work. And so you need to be really careful when you do this that you don't change the semantic meaning of what that grammar is showing. And that's really hard. They're also typically limited to context-free grammars or regular, specifically with text-based input. And this is great if that's what you're looking to test. But if you're trying to do binary file formats or network protocols that are all binary-based, you're typically pretty limited in what you can do with these tools because they just don't give you the freedom to express that language. So what can we do to do better? As I said earlier, one of the things that is a big problem is the ability to build custom test harnesses. Most fuzzers and tools out there that are in this vein, like I said, they look for very specific things. Did I crash the application? What's the return type? What signal did it throw at the end? And so being able to have more flexibility in terms of determining, am I seeing something interesting? And determining, is there something interesting I can get out of this? Is there some information that's sharing? Is it leaking that I can determine something more from? Being able to directly use the grammar from our parser is great. If I've already gone through the process of writing a parser, so in the instance of one of the reasons I built this is we built our own implementations of a handful of different SQL parsers because we needed it for an analysis tool. And one of the big problems we're trying to figure out is how close is our grammar to the original one? What do we parse and how does it affect, how similar is it to the real one? And if we were to go and take this 15,000 line grammar definition and convert it over to the grammar definition that, say, Dharma uses, we're not going to be able to manage that. As we make changes in one, we're not going to be able to go and update it and keep them in sync, and we'll never be able to really know that we're doing the right thing here. Expressivity is another one, as I said. Having the ability to do these common things like text-based, context-free, and regular, but having more than that. Being able to really hit the binary stuff. If we want to do like complex file formats, like ELF files or PE files where there are fixed offsets in there that need to be correct so they can go to the right place and get information. So being able to have that breadth and do more with it is something really important. Being able to use it from other languages, this is another thing. There's a lot of tooling, especially for parser combinators, where it's built for a specific language. Like for instance, Antler was built for Java, and there's a lot of really good tooling for it in Java. But as soon as you deviate from that platform, getting access to that tooling is pretty difficult. What if you could use this in Java, but also use it in Ruby or Python and Go? So having that flexibility to use this, this code base from anywhere would be really helpful. And as I said, reusing as much as possible. Let's avoid duplication, because when we start talking about inputs this large, there's no way we can keep track of this. We need to make sure that we're using like the original source material, and we're not going to get into the place where we have to manage multiple ones. So as I said, this has been released since around DEF CON. The architecture ends up looking something like this. At the base, you have SynFuzz, which is, it functions mostly as an intermediate representation. So you build front ends that will recognize individual grammar languages. So you could have one for Antler, one for Ragle, one for eBNF, Bison. And what these do is it reads in a grammar file for their specified format, and then will translate that to the SynFuzz syntax tree. And then from there, you can generate test cases and use that to build your own test runners. And so by making this code-based and making it so that you don't have to, it's very much not out of the box like you would get from something like, say, AFL, where it will just run on a binary and fill in stuff for you. But it allows you flexibility in that you can build a lot of your own tooling and look for very specific things. And we'll look at how we're going to do that in a few minutes. But the important thing to note is that we can build tools like that from this. And the idea with this is that you should only ever have to write your own test harnesses. You shouldn't have to write your own front ends. Those will be built for you. Right now, Antler exists, and I'm planning on building out more. So let's take a look at how this works and how you might do it. At the most basic level, you get the combinator interface that SynFuzz provides you. And this is how you express a grammar, and any front end will end up converting. So this is writing in the pure combinator language within Rust. And if you've ever worked with the combinator library, it will look probably pretty familiar to you. At the top here, we're declaring a generator for a number, which is essentially just a sequence of the numbers 1 to 9, and then a sequence followed by 0 or more of 0 to 9. And so what this is doing is building up an expression. So something like number plus number or number times number, as complex as you want to go from there. So we have our operators, we have our numbers, and then we have the expression that combines all that together. To use this, we can go a little bit deeper, and we can use one of the front ends. This is the Antler one. And so this is essentially all that's really required is you provide it a grammar file, you read it in, you generate the rules from it, which is basically just parsing it and then translating it into the intermediate representation. And then you can pick a starting point. So in my case right here, I'm using the node root. So that's like the top of the tree. But if you wanted to say generate just some subsection of that grammar, you can say, I want you to start here. And it will build you a tree down from there and just generate subsections of that language. Below that, it just kind of gets you the string out of there, and it will print it out. This is like the most basic example. You can pretty much use any method you want for pushing this into a program. The full socket API, if you want to, so if you want to send it over the network, you're good. You get pipes, files, anything you can use at the operating system level, you have the flexibility to use with this. Let me see if I can see the right one. So as you can see here, this is the executable showing the very first example that I showed. This is the expression, and you can see me running it multiple times here, and it's... Is that super blurry? Is it the projector?
No, it's really, really small. The projector only has so much resolution, so it's hard for me to get that to work. If you blow it up, it might be visible.
Let me see if I can do that. Cool, okay. So as you can see here, it's just running through, and every single iteration it takes, it will generate you a new string. 100% random, it's coming from that grammar we fed it, and it will give you a new one every single time, so long as the randomness doesn't generate the same values. So we've seen how we can use this now. Let's talk about designing test harnesses, because that's really where we're probably going to spend a lot of the time using a tool like this. At the most basic level, this is like what we typically see most fuzzers doing is, did it crash? Did it do something that is like considered bad? So to do this, we can use something like popen or exec. We start the process. We generate some input using the code snippet that I showed earlier. And we feed it into the application using whatever mechanism, whether it's a socket or a pipe or standard in or argument or environment variable. And then we listen for it to end. Does it halt? Does it halt with a signal that we understand? Is it a seg fault? Is it seg abort? Did it do something interesting that we can do? And this is essentially the state of where we are with most common fuzzers today. We can replicate that functionality by doing something just like this. Once this happens, we analyze the crash. We see if it did something interesting. Do we have access to modify the instruction pointer? Can we take control of this? The answer is yes. Cool, we found something interesting. Let's go a little bit more esoteric, a little bit more interesting, something that we can do that you can't typically do with one of the off-the-shelf fuzzers today. As I said before, one of the main reasons for building this was to test reimplementations of parsers that we didn't know if we were going to be replicating the correct behavior. How do we determine if our implementation is overfit? The case that we are parsing things that the reference implementation doesn't. So one of the ways you can do that is you set up your test harness the same way. You generate a test case, and you need to find an oracle. And what I mean by oracle is it's some mechanism for determining whether the error that you're getting back is either a syntax error or a runtime error. If it's a syntax error, then it means that the grammar that you fed it and generated input from is going to be not the same as the one you're testing against. You have generated something that your grammar says is valid, but the reference one does not. If it's a runtime error, there could be some state involved where you generated something that passes the parsing phase, but there's something about the internal state of what's going on that is not semantically correct. So once you find an oracle that will provide that information to you, you can use that to make those decisions. So one example of this is something like in MySQL. There's two examples here of errors you might get from sending a SQL query to MySQL. The top one here is a syntax error, where it specifically says there's an error in your syntax, and it shows you kind of where it happened. And this is a case where we wrote something that never passed the parsing phase. If you go below it, you'll see a runtime error. The table MySQL A does not exist. And this means it finished parsing, it validated the sentence. The sentence is a correct sentence in that language, but something in the state, the database, the schema, it's not meaningful. There's something wrong with the statement, but we know we got past that. So we're getting to the interesting points of the application, which means that we're not overfit. Cool. The converse, you have underfit. Does the reference implementation generate sentences that are something that our parser does not match? If we have access to the actual grammar, we can do the opposite, where we generate from the reference implementation. So in the case of open source software, if you get access to that, You can generate from there and feed it into yours. If yours comes back and says this isn't valid, then it's something that's underfit. So, quick other demo. I don't know that I can get this visible. So this is an example testing actual MySQL. So I used the public available MySQL grammar for Antler and built a test harness around that same methodology where it will basically generate and then send to there and then identify the error message coming back and determine if it is a syntax error or some type of runtime error. So here I'm feeding it in a starting path of create table. So it's going to generate me a whole bunch of statements that are create table statements. And you can see here on the left, there's no tables there. I'm going to hit play, and it's going to go through the process. Cool. So it's running there on the right, and it's just iterating through those create statements. You'll see it spitting out syntax errors. Those are all strings it generated that it passed to the MySQL database, and the database said this is a syntax error. So there are clearly issues with the grammar that were being used. You also see on the left-hand side, it goes from having 0 tables to like 1,000. So it's pretty quick in generating these values. What would I just do? So what's ready today? You have access to Synfuzz. This is a public open source project that I'm still working on. There's a ton of stuff happening on it in terms of getting more front ends built out for it, as well as adding more functionality to it. Some of the things I'm working on right now is cycle detection and forcing progression. So you can get into places where there are significant amounts of recursion that can cause Stack Overflows. So fixing that problem and making it possible to use very recursive grammars. Exposing C bindings and other language bindings so you can actually bring this into any language you'd want to. Negation logic is complicated. Context sensitive and introspective grammars and functionality to handle that. And then grammar coverage information, so understanding how much of the grammar we've explored and what we've generated from there, and the ability to tune that. Cool. That's it. Thank you.
Oh, this one. All right.
Okay, so it's going in real loud.
That's right. That works.
I think we're good.
Cool.
Thanks for covering.
No worries. Have a good one.
We'll see you tonight.
Yeah, I'm out of the spray zone.
Y'all wouldn't mind getting together, like, those spaces between, that'd be awesome.
Holy crap, we have a bunch of people that actually like me. What the hell's going on? Yeah, apparently. I think you're all here to see an expert, but you're probably sorely mistaken. Holy shit. How's it going? I'm actually kind of shocked with how many people are showing up to this talk. Holy crap. You guys all think you're here to see some sort of expert or something. You're probably mistaken. It's all about my slippers. That's what you guys are here for. Slippers and the towel. right. There we go. Let's go do this correctly now. Can I prop this up somehow? Nope. Nope. Are you propping my crap up? Ah. No, that'll work. Nah. Gorilla tape, yeah, don't worry about it. I'll just paddle you later on camera. Huh? All right, we got everyone here? And am I about ready? Yeah, screw it. Everyone ready? Cool, fantastic. So, I am Evil Mog. Apparently I know things and you're all here to see my lovely talk. You're here to see an expert. You're probably sorely mistaken, but that's all right. So we're here to talk about esoteric Hashcat attacks. So we'll start with some of the, come on, click. There we go. So I'm Evil Mog. I'm the Bishop of the Church of Wi-Fi version 3 or any greater version. I'm a member of Team Hashcat. I apparently consult for X-Force Red and hence all the pretty branding. I have a bunch of certifications. Somehow I got my OSCE. I have no idea how. Apparently I do pyrotechnics for fun while we're at it. I'm a network monkey, server monkey, pentest monkey, doer-ish stuff. I'm the chief shenanigan officer for DerbyCon, which is not a real title, so I'm not a real DerbyCon volunteer. Do research, yada yada, all the stupid stuff. This disclaimer, I have to read this one out because IBM Legal will kill me if not. So, I am not a lawyer. Opinions expressed in this talk have not been vetted by IBM or any of its subsidiary companies. Views and opinions expressed are mine and mine alone. I'm not representing the Church of Wi-Fi, nor am I representing Team Hashcat in this talk. No warranties expressed or implied. Consult a professional. I'm not responsible if you set your house on fire, spike your electric bill, or otherwise break stuff. Practice techniques shown on systems you control and are authorized to penetration test, and don't steal dumps illegally. With that said, why the hell are we here? So some of us have more horsepower than brains, and we work with really fast hashes. So we do stuff like NTLM, MD4, MD5, SHA-1, SHA-256, Landman, SCP-B code, all the stuff where you get like 320 billion keys per second, and you run out of, when you hit that 90% mark, you need to find new attacks to get beyond 90%. So I like to get creative. This talk is all about the YOLO, so much YOLO. So I'm going to assume you all know how to use attack mode 0, which is straight wordless attack, mode 1 combinators. I assume you know how to use mask attacks, hybrid attack mode 6, mode 7. This is not a Hashcat 101 talk, and I also assume you're using Linux. I don't discriminate against Windows, but most of us use Linux or Mac when you're cracking hashes. So, we're going to talk about the infinite monkey theory of password cracking. So, infinite monkeys at infinite keyboards will eventually type your password. Unfortunately, we don't have infinite monkeys or infinite keyboards unless you're RenderMan back there. But we do have GPUs and fast hashes, which is good enough. So the trick to keeping a large cluster happy is throwing shit against a wall and seeing what sticks. Try random things. The nice part is Hashcat is fully pipelinable, so you can do really weird stuff with it. So, raking. This is a technique that has been around for the last 5-6 years. It's how generated 2.rule was created, but no one documented how raking works. So we got some example code here, and by the way, all this stuff is on my GitHub, so you can go download all this at the end of it. But we're going to walk through this example. So what raking you do is you say start a sequence of 1 to 100. So you loop over this Hashcat attack, and you go and you set up, say, workload profile 3, so you're going to run really fast. Don't run this on your home theater PC. We're going to use attack mode NTLM, where you do it on the straight wordless attack. Tell it what your hash list is, and loop over all of your dictionaries, and I mean all of them. So grab 30, 40 dictionaries, throw it in a rule or throw it in a directory, generate 100,000 rules. And then we're going to turn on debug mode. What debug mode does is it will capture the original rule, it will capture the rule it will capture the original word, the rule you cracked on, and then the resulting output. We're going to collect all of these. You're going to loop it over 100 times. We're then going to run cut. We're going to create a debug.rule file, a debug.dict file, then re-execute that attack. This is exactly how generated2.rule was created, because we sat there looping over all of our hash lists for 6 months. This is back in 2012. So this is basic raking. It hasn't shown up in anyone's hash techniques list. It's talked about on IRC once in a while. It's a really effective technique, and it should be done by more folks. I'm hoping someone creates a better generated2.rule file, because mine kind of sucked and was created 6 years ago. So next technique we're going to talk about, if we get really bored, is cut B. So this is someone dropped a blog, Rants by Chort, back in 2012. We've simplified his technique a little bit because his original script didn't really work 100%, so you need some tweaking to it. So what we're doing is we set a couple of paths. We then loop over a sequence. So what password splicing is say you have the password of 123 password. We will take number 1, we'll take 12, we'll take 123, 123 PA, loop all the way through. That's a traditional cut B attack. So what this does is you can say you've got a giant hashcat pot file, about 2-3 megs, and you were trying to go set up an expander attack. When you're using a cut B style attack, you can do some interesting brute force by taking existing patterns on things, like say you have 2018 in a password, it'll get auto appended for you. Now this technique works fairly well. Not many people do it, and you can process all your word lists. But we're going to show an advanced technique I created later on that's an enhancement to cut B that will decimate your password hashes. So that's cut B. Who here knows what expander is by a show of hands throughout the room? Probably everybody, right? How many people here modify expander? Because expander by default only gives you a character output when you run your passwords through. So say you take your dump, you're going to get maximum 8 characters on an A1 attack. Every time you download Hashcat utilities, go open up the expander.c file, change length max from 4 to 8, then recompile the code. You will get far better results, but we leave this as a default because Adam one day decided it was more efficient to go with 4, not 8, but it gets terrible coverage. Little known trick, something that should be done by almost everybody. Add this to your tickle trunk. Now, this is the EvilMog secret sauce that tends to get me passwords correct left, right, and center. I call this my blender. So what we're going to do is we're going to take your Hashcat pot file. We are going to cut using the colon for a delimiter. And now a secret we've got on this is a lot of people will stop your cut at the first colon. The problem is if someone has a colon in their password, you're not going to get the rest of the passwords, so your cracks are going to be incomplete. So you go -F2-, take the pot file, put it into a can.list. We run a standard cut B on it, forward and back, and then if you want to go really fancy, we run expander through it. So we take the output of your cut B, re-expand it, and attach. You'll get a lot of crap, and it takes your word list from, let's call it 4 megs, and it increases it to about 200 megs. But when you've got 8 GTX 1080s, it still only takes 9 minutes. And you crack another 10-20% on your password dump. Works fairly well. We're going to actually make this even better on the next couple of slides. But stuff like this is also in the GitHub, so it works fairly well. So our next technique, Purple Rain. Somebody modified raking to make my life really easy. So basically what raking is, you take a word list and you shuffle it. And the reason why you shuffle it is Adam wrote a tool called the Prince Processor, and it's basically a candidate password generator. The thing with Prince is if you give it the same output in the same order, you'll get the same results out of it. But if you shuffle the word list, it generates completely different candidates. So you shuffle, say, rocku.txt, you pipe it into Prince Processor, you pipe it into Hashcat, generate 100,000 rules and turn on debug mode, and you'll sit there and let it literally sit there for 3 days or so, and you'll crack a ridiculous amount of hashes. Just burn the horsepower. It's stuff you try when you have nothing else to do. And if you want to go collect the hashes afterwards, we call it Purple Rain Barrel. And this was revolutionary because if you do this on an NTLM version 2 hash, you'll probably crack it in the user world. Now, The other thing is, like, he was talking about how Hashcat is pipelinable. So, and all the Hashcat utilities are fully pipelinable. So we can do things like take permute, pipe it into prepare, pipe it into Prince processor. So Jeremy got liquored one day for his class and figured, why don't we pipe the output of Prince processor into Prince processor, then pipe it into Hashcat, and we call it Prinception. And oddly enough, this actually works. So this example we have on here is we're going to shuffle rocku.txt. We're going to pipe it into Prince processor, pipe it into Prince processor, pipe it into Hashcat, generate 100,000 rules, and just let it sit there. Check on it in about a week. If you take this on your average corporate Active Directory dump, you'll go from, let's call it 40% hash crack to about 80 overnight. This also works well on NTLM version 2. I don't recommend doing this on a slow hash. Try this on bcrypt. You'll be very, very, very sorry. Do this on NTLM, SHA-1, MD5, MD4, anything reasonably fast. Even NTLM version 1 or version 2, it should be okay. Just don't try anything like that's salted and slow, because, yeah, you'll probably spike your electric bill. So that's Prinception. So let's kick this up yet another notch. How about we take cut B output, feed it into Prince processor with 100,000 rules, see what happens. Because why not? So we don't need this bash script because it really doesn't do anything, but I just get lazy on my pipelines and don't feel like shuffling members of my shuffle command. So all we're doing is we're basically shuffling our can.cutb file we created earlier, pipe it to Prince processor, pipe it into Hashcat, generate rules, give it a pot file path, give it your usernames if you've got your things formatted the incorrect way, and away you go. So this one gets even more creative. Now, mask generation. Who here creates masks in all their candidate files? Probably not many of you. So tool came out aeons ago called Pack. The newest version on GitHub works fairly well. What we effectively do is you feed a bunch of word lists or your candidate files in and you create masks based on them. So this is a basic mask generation, but the problem is you need to figure out how many packets per second you're running, have things finish in a reasonable period of time. So with my methodology, I set, say, 160 billion keys per second with a 360-second runtime for my maximum mask time. And I run this over not just my candidate.list, I run it through my expanded versions and my cut B versions. So if you run it just off the passage you cracked, you're not going to get much. But if you run it through Expander, all of a sudden you're expanding your key space without resorting to straight out brute force. So run it over your expanded files or your cut B files. So that, it works not bad, but what about hybrid mode? Who here still uses mode 6 and mode 7? If you don't, you probably should. So what do you do to figure out what people are appending their passwords with? Well, let's set the minimum length of 3, maximum length of 8, and redo that same style of an attack. Then use those in mode A6, A7. Don't just run it on your passwords, run it on your expanded, and it gets you some really interesting patterns. These will take you a week or two to run, but hey, you guys run your corporate Active Directory audits once every quarter or so. You can let it sit there for a couple of months for grins. God knows the attackers are. I mean, I collect my Active Directory hashes for years, and we go crack them later whenever I think of random stuff to try at 3 in the morning because I got no life. So, here's a typical A6 attack. We run Hashcat in mode 1000, so NTLM. Run it through your combined.ntlm file, which is our hash file in this case. Workload profile 3, mode A6. On the left side is my candidate.cutb file that I created earlier. Right side is my hybrid sorted mask I just created from that script. Turn on optimized mode and put on a box. The nice part is if you have 50, 60 nodes with multiple GPUs on them each, take a spare node, take it off in the corner, let it crack something, forget about it. It's like a good fine wine. Check on it in a couple of months, see what comes out. And here's some of the passwords we're getting out of this thing. It's actually rather creative. You got things like Unicorn 2016, MAAB 2018, Luke 2239. You get some weird stuff on here, and this is from an actual thing we extracted from hashes.org or some other legal repository of hashes. And this is all using these techniques in this slide. So I invented a new cut B technique, and I'm rather proud of this because I was trying to fill content for this talk. Ran out of time or ran out of content, and I'm like, hey, everyone who does cut B doesn't handle things in a very particular way. So we'll go back to the example of 123 password. If you're running a password splice on this, you'll start off with 1, 1, 2, 1, 2, 3, 1, 2, 3 PA, etc. When I'm done this, what we do is we stop at that, we increment the sequence, and then we go with 2, 2, 3, 2, 3 PA, and expand your pattern components. I figured out this only expands our hashcat files for cut B by 30, 40%, but it was cracking that many more passwords and only taking still 9 minutes on a rig. So this is actually incredibly effective, and as far as I can tell from all my Googling, no one knows, or no one's documented how this actually works. Sorry about that. So the starting of the script, it's relatively easy. We do a cut file. We do cut-d, which sets, here's our sequence number, or our delimiter of a colon. We rip apart the cashcat file, pipe it out through a candidate.list. We start off a quick little loop through 1 through 8. You can modify this if you want to go with 1 through 9, 1 through 10 for your sequencing. Then a little bit of bash magic basically allows us to do negatives or increment this in a loop. So what this does is it restarts the sequence. So it goes 1 through 8, then it starts 2 through 8, etc., all the way through. So it'll loop through and expand your candidate pieces. I haven't figured out how to make the negative side work yet, so I'm working on that piece. That update should hit Hashcat when I get liquored at the bar here at DerbyCon, probably in a couple hours. So watch out for my GitHub. We then cat all the files together, run them through Expander, and create your files. So this one's relatively effective. And then if you really want to go hardcore, run Expander after it all and re-expand all your outputs, just because why not? And if you really want to get bored, take Expander and pipe the output of Expander into Expander. Just try stuff like that. I mean, I get up one day and I'm like, hey, I want to go pipe Expander in through permute, in through prepare, in through sort unique, then back into Prince processor and into Hashcat after piping it through shuffle a couple of times. Just try random things. The weird part is we don't want to resort to brute force, but sometimes you just get you'll get a writer's block almost when you're trying to crack a hash and you're trying to figure out what's cracking this, and entropy is your friend. Get out of that mold, try something random. I mean, I've done some weird stuff like piping music lyrics in through Expander, in through cut B, in through rule files, and then re-cutting them up with cut B and Expander again, then piping to Prince processor. Just go do random stuff. That's the point. These techniques are going to change all day long, but users, even though they are reasonably predictable, they do some random things like looking around. So if you can kind of predict how users are creating their passwords, you'll get far more effective. So that's what this whole kind of talk came down to. And here's a comparison of the file sizes, right? Like our standard candidate file started off at 2.6 megs. The expanded version are 189 megs. And 189 megs on an NTLM A1 attack, and that still takes, like I said, 9 minutes on 8 GPUs. If you're running this at home, less than an hour. And you get far more results. So try some of these techniques in the future for your next one. And now the best part is, while I'm at it, all this stuff is on GitHub. So feel free to rip apart the shell scripts, send me pull requests, play with stuff. My code of conduct is simple. If your code's good, it's good. Don't be a jerk on the mailing list if there is one, because there isn't. And hit me up on Twitter, and feel free to join the Church of Wi-Fi and watch our shenanigans at Hacker Jeopardy later on tonight. Questions now that I'm done? Thank you, by the way. Thank you all for showing up and listening to my rant. So, questions? No? Perfect. You guys all rock. Awesome.